Are we live?
Just give us a sec.
Give us a second to check if we're live. And
Hit the button.
I did hit the button.
Ooh.
Looks like we're live. Okay, audio good. Audio's great. All right, hello everyone, and welcome to the MATH2801-2901 Statistics revision seminar. My name is Matthew, and I'm going to be your, host for the first part of this seminar. After me is going to be Otto, and then Catherine. We're going to have 3 people taking this workshop, and I think my part should cover an introduction to probability, an introduction to random variables, and common distributions. So that's going to be me, and my, my name is, I don't like this, is Matthew. And then we're going to have these 2 things. Today are going to be Otto. And tomorrow Otto is going to start off the workshop, and then Catherine is going to finish the course. All right, so let's get started. So, first thing, introduction to probability. We've got a couple definitions that we just kind of have to know. So first thing is an outcome. Oh, that is a little bit too fat. Here we are. So an outcome is the result of an experiment. So maybe rolling 1 on a die, or if you had like a ruler, you could measure like, 20 centimeters. That's the outcome of an experiment. And the sample space is the set of all possible outcomes. So on a die, it would be like the set 1, 2, 3, 4, 5, and 6. And an event is a set of outcomes with an assigned probability. So we can say, hey, I'm going to call an event if I roll an even number. So an even number is just going to be a subset of the sample space where I can define some kind of probability. Very fundamental thing here is a probability function. So a probability function is a function that returns the probability of an event. So if I defined that probability, an event being I roll an even number on a die, this probability function will tell me the likelihood of that, which is just 1/2. So things about probability functions, all probabilities lie between 0 and 1 inclusive. So that just really means any probability that we have in statistics is always going to be either between it's not going to happen or it's always going to happen. The probability of the sample space is 1. So if we've truly described every possible outcome of an experiment, when we do that experiment, we're always going to find one of those outcomes. So the probability of the sample space is 1. The probability of any event and its complement add up to 1. So this is just some fundamental thing in mathematics where if you have A and not A, then one of those is going to happen. So if we have an event and the complement, which is not that event, we will always get either the event or we won't get the event. That's what that means. Cool. For any 2 events, we have this additive law. So whenever we see some function in statistics or in mathematics, we always want to figure out exactly how do we manipulate that function. And this is one of the identities that we have for the probability function. So we have that the probability of A plus the probability of B minus the probability of A intersect B is equal to the probability of A union B. Right, so I guess this is kind of important. So something in probability is that I will often draw these little diagrams, and these are just Venn diagrams, and the areas of each of these spaces corresponds to, I guess, the magnitude, the size of the probability. So if I call this left event A and this right event B, then the probability of A is around about equal to the probability of B because I have drawn the areas to be around about equal. All right, but it also gives some intuition for this additive law. We can say that the probability of A union B, so the probability of, you have to forgive me for the poor writing, the probability of A union B is this thing. So how do we get that? Well, we can just add up the probabilities from A, and then we can add the probabilities from B. And then we can, well, then we've double counted this center. So we need to subtract it off. And that's where this law comes from. Okay. Other thing, the probability of the empty set is 0. So really, we just introduced this so we can start talking about the probability of, we can start talking about events that are mutually exclusive. So this is the definition of if something is mutually exclusive, is that their intersection is 0. So I guess maybe we draw a picture. We say A and B are mutually exclusive if they do not overlap. So A and B, and I guess this is the whole sample space. So these events would be mutually exclusive because there's no overlap. After we start talking about this, we can start talking about ideas of conditional probability. So conditional probability is something that you may have started learning in first year. It says, hey, what's the probability of A given that I already know that B has happened? Right, so we say, I guess we write, we say this expression as the probability of A given B. And it's just equal to the probability of A intersect B divided by the probability of B. And of course, the probability of B has to be greater than 0, because if it was equal to 0, we would be dividing by 0, and that's a huge issue. And of course, it's a probability, so it also has to be between 0 and 1. All right, so that's just a formula. I guess we could look at some kind of intuition for it. Again, drawing out these Venn diagrams, we could have, oh, that's awful. I don't like that. We could have something that looks like A and B. So we're saying, hey, I'm gonna continue the, I'll just write it out. So we have A and B. So we could say, hey, given that we're in B, this becomes our whole sample space. And so the probability of A, oh my God, just becomes the ratio of this area to the area of the whole B space, which we already know we're in. That's just kind of like a quick little, sanity check. We get the multiplicative law. So we just take this expression and we multiply B across to the top here. And so we say that, so we get this expression. The probability of A intersect B is equal to the probability of A given B times the probability of B. We could also do something which is that the probability of B intersect A equals the probability of, right, I'm just like mixing these around, is equal to the probability of B given A times the probability of A. Right, this is the same thing, but I've just switched A and B around. Cool, so you can imagine instead of writing a B here, I could write something like B intersect C. B intersect C. If I do that, I can follow the mathematics and I can just figure out this formula. You can also think of this formula kind of intuitively. You can say, hey, let's have a look at our Venn diagram. We can say, hey, I'm going to, we can think of this formula, we can remember this formula as saying like, hey, this bit gives us, make sure that we're in the circle C. So we're in the circle C. And then the next term in this sequence says, hey, given that we're in circle C, what's the probability that we're in circle B? So it kind of pushes us into B. So if this was B, then it pushes us into this intersection. And then the third thing says, hey, if we're in B intersect C, what's the probability that we're in A? And so that kind of pushes us back into this center. Oops. Right, so that's just a formula that you might have to just remember for the probability of A intersect B intersect C, so 3 events. We have a question. How do you find the PDF of the product of 2 random variables given that PDFs? I think that's going to be something for a little bit later in this revision seminar. So I guess we'll keep that in mind, and we'll come back to that question when it becomes relevant. Cool. So 2 events are independent. So we have this definition of independence, which is that 2 events are independent if the probability of the intersection is equal to the multiplied probabilities. Right, well, we just had this formula for an intersection. Or rather, we just had this formula. So if we put this definition into the formula, well, then what do we get? We get the probability of A given B equals the probability of A intersect B divided by the probability of B. Well, we can say that this is equal to the probability of A, probability of B, and then divide by probability of B. That just equals the probability of A. Right, so that's kind of a definition of independence. And of course, that makes sense. If 2 events are independent, if I know something about one of the events, I should gain no information about the other event. So this is just like a good sanity check to make sure that our definition of independence lines up with exactly what we think it should mean. All right, this is a introduction. We're going to do a question now. So let's do this question. Let A and B be 2 events in some sample space with the probability of A greater than 0 and probability of B greater than 0. So show that if A and B are independent, so maybe we should write down the definition of independence first. So that is the probability of A intersect B equals probability of A, probability of B. They cannot be mutually exclusive. Right, so what's the definition of mutually exclusive? So mutually exclusive, we can write that as the probability of A intersect B equals 0. So for this first question, what we can say is, well, we know that probability of A and probability of B are both greater than 0. So if they're mutually exclusive, we know that this holds. And that means that we know that the probability of A intersect B is greater than 0, which of course means it's not equal to 0. And that concludes the proof of this first bit, is just, hey, we know that the probabilities are greater than 0, so they're not 0. All right, that's part I. Let's go part double I. Show that if A and B are mutually exclusive, so this is like the exact same question, but we have changed the order. Show that if A and B are mutually exclusive, then they cannot be independent. So let's write this out a little bit better, is just say we assume that the probability of A intersect B is equal to 0. So, or maybe that's what we know, and then we can say, well, suppose that they were. Suppose that they were independent. Then the probability, then the probability of, oh my god. Then the probability of A intersect B is going to equal the probability of A, probability of B. But we know that that's greater than 0, so that would imply that the probability of A intersect B is non-zero. which of course we know is not true, so we have a contradiction. Right, so therefore, if A and B are mutually exclusive, they cannot be independent. Suppose that A and B are mutually exclusive. Find A given A union B in terms of PA and PB. Well, for this, it's just a very standard like sub into the definition question. So let's sub into the definition. So we have the probability of A given A union B equals, well, this is just the probability of A intersect A union B divided by the probability of A union B. Right. But we know that A and B are mutually exclusive. So the probability of A union B is just going to equal the probability of A plus the probability of B. And we know that just because we can draw out our Venn diagram. So if they're mutually exclusive, things look like that. We have A, we have B. And the probability of the union is just going to be the sum. Right. Now, what about the probability of A intersect A union B? Well, that's just going to equal the probability of A. Reason for that is, hey, what's the probability of again, we can just go back to our Venn diagram and we can say that the if we intersect A with A union B, so we're intersecting A with both A and B, well, then we're just going to get A back. So it's just the probability of A. I hope that makes sense. Here's something a little bit more formally written out, just so if you're a little bit confused by any step, we can you know, just have a look at something a little bit more formally written. We have this definition here of pairwise independence. So two events are pairwise independent, or a set of events is pairwise independent, if for all AI and AJ, the probability of AI intersect AJ equals the probability of AI multiplied by the probability of AJ, for all I not equal to j. Right, so, well, we just saw that two events are independent if the probability of A intersect B equals the probability of A intersect times the probability of B. So this is just like a generalization of pairwise independence. We also have this idea of mutual independence. We say that a set of events is mutually independent if the probability of A1 intersect A2 intersect all the way up to AN is equal to the product. Right, so this is a further generalization just for a set of events that are n large, so a set of n events. And I guess something that you can show is that mutual independence implies pairwise independence, but pairwise independence does not imply, I think that should say mutual independence. So that should probably say mutual independence. Okay. That's something that is just something you can show. It's not terribly interesting, but it is something that we can say like mutual independence is a stronger condition than pairwise independence. Law of total probability. So this is just a formula that you kind of have to memorize, which basically says, hey, if we have a partition, so let's remind ourselves what the definition of a partition is. A partition is if we have a set of events and the sum of the AIs, the probabilities of the AIs equals 1. So in particular, that equals the probability of the sample space. Then we say that the set of events AI forms a partition on the sample space. And for any event B, we have this formula. Oops, that has made a mistake. We have this formula. Okay. So we can draw this out. We have our event B, which I've just written, and a partition, which basically cuts the sample space into a set of events, and we say, hey, the probability of the event B is just going to be equal to the combination of all the probabilities from each of the events. That's all this law of total probability is saying. Anything else about this? I guess just for your culture. Oh, you know what? No, I won't say that. We've got enough to learn today, and we don't need anything more complicated than what we already have. So, let's say that A can be partitioned, then we get this thing called Bayes' theorem. Bayes' theorem basically just is a way, so the purpose of Bayes' theorem is to take the probability of A given B and write it in terms of the probability of B given A. And we can do this just with a couple of the identities that we've already discussed. So if we use the law of total probability, and if we go back up to this conditional probability formula, I guess here, we can combine those two, or we might even want to use this one. And we can derive Bayes' formula, Bayes' theorem. It's worth making sure that you can do that yourself. It's a good little practice. I would say that something about Bayes' theorem is whenever you're in an exam and you see a question about diseases, or the probability that a test runs up positive if the patient is really negative. These are the kinds of questions that people love to ask about Bayes' theorem. So if you see anything about diseases, you can pretty much be certain that Bayes' theorem is going to pop up. All right, we've spent a little while on our introduction to probability. So I guess we'd better get over to an introduction to random variables. I'm just gonna have a little quick water break. All right, so introduction to random variables. A random variable is a variable whose value depends on the outcomes of a random experiment. Right, so in the notes, if we're looking at the same notes, you will have to see a lot of like weird definitions that look at like A of omega is less than omega. These are all like very complicated ways of writing down this definition. They are technically more like mathematically rigorous, but they just hide the fact that a random variable is a variable whose value depends on the outcome of an experiment. We denote random variables with capital letters, so I might say capital X or cap X, and distinguish them from deterministic variables like X. Something of note is that we also use numerical random variables. Random variables. For the most part in this course, you can imagine that you could create a variable which is not numerical. We use it sometimes in examples, so we say that X is equal to heads wins if heads wins, and X is equal to tails wins if tails wins. Those aren't numerical random variables, but for the most part in this course we will just be using numerical random variables. All right, so a cumulative distribution function, or CDF, of a random variable X is defined by we give it cap F underscore, or cap F subscript cap X of X equals the probability that X is less than or equal to X. Okay, that's a big mouthful. Basically, the thing that you want to think about when you're thinking about cumulative distribution functions is a graph. You could have some distribution. Let's say it looks like this. And the cumulative distribution function is going to be equal to the probability that X, so let's say that this X is your random variable. let's say that this is your, I guess, threshold, and this is the axis of your random variable. It's the probability that your random variable takes a value less than or equal to some threshold. Okay? Using CDFs. So I think this is something that we've talked about already, but whenever we see a new function in mathematics, we want to know how to manipulate it. And here are a couple identities for how we manipulate these functions. So we can take 1 minus the cumulative distribution function, and that's just going to be the probability that x is greater than x. So if we go back to this, expression, or to the diagram, we can say that, hey, if the area of the whole distribution is equal to 1, and we subtract off this bit, then all we are left with is this bit. And of course, we have to think about if we're including x or not. So if we're having a discrete random variable, then including x and not including x is going to make a difference. So that's just something to note. Similarly, we can do the same trick for the probability that capital X is between little x and little y. And that's just going to be the cumulative distribution function of the bigger variable, subtract off the cumulative distribution function of the smaller variable. And it's for this exact same reason. So I could imagine that if x is my little variable, I could call this thing over here y. And so instead of, so I take the area, which is just here, and I subtract off this area. And so then I am left with just this area in the center. Cool. That's just some, I guess we'd call that algebra, or just manipulation of cumulative distribution functions. We have a couple more properties. So a cumulative distribution function, well, what does it look like? Generally, it'll look something like this, where it goes up to 1 and 0 at positive and negative infinity. It is non-decreasing, so it's always increasing. That's really important. And it's right continuous. Right, these just come from the definition. And shouldn't be too difficult to understand. All right, so a random variable is discrete. So I guess we've talked about CDFs, but now I guess we're going to start talking about different types of random variables. So we have a discrete random variable, which is a random variable, so that takes a countable number of values, that can take a countable number of values. So you could imagine, I don't know, the outcomes on a die is always going to be discrete. So if we have a random variable that depends on the outcomes of rolling a die, then that random variable is going to be discrete as well. We have this definition for the probability mass function. So the probability that x is equal to x is called the probability mass function, and it's related to the cumulative distribution function, so the CDF, by the following relationship. So all that means is that we're just summing up all the values of y where it's less than x, and that just exactly corresponds to our definition where we said that this was the probability that x was less than or equal to x, right? So these are exactly equivalent. Okay. Continuous random variable. A random variable is continuous if it can take a continuum of values. So if you were measuring, I don't know, the position of something in x, y, z space, x can take on any value depending on how accurate you want to be. That's what a continuous random variable is. It's just an outcome of an experiment where the outcome can be a continuous value. The probability density function of a continuous random variable is related to is going to be equal to the probability that x is between two values. So whereas before we had it's the probability that x equals some value, for a continuous random variable, the probability that the experiment winds up with a single exact value is always going to be 0, right? Because the probability of the area under a single point is 0. Right, so whenever we're using continuous random variables, we always have to look at what is the probability that our random variable takes a value between two thresholds. Okay. We have this definition. So the PDF is equal to the integral of the fx of the distribution. Importantly, we have the cumulative distribution function is equal to the integral from -infinity up to x of the distribution, and the derivative of the cumulative distribution function equals the distribution itself. Right, you can almost think of this as like these are just the definitions. Right, so I'm sure these are things that everyone will have or had memorized for the midterm, so hopefully this is not you can remember these things. Expectations. So one of the important things in this part of the course is being able to deal with expectation values. So what is an expectation value? It is we take the expectation value of a random variable x is its mean or average. So depending on how thorough Gary has been in the lectures, he may have talked about the difference between a mean and an average. The expectation value, I believe, is a mean, or is it? I think it's a mean, and not an average. I think the mean is more closely related to like a true mean, whereas the average is more like a sample average. So averages are more like contextually related to samples, and means are more contextually related to, I guess, the true distribution. For a discrete random variable, we have the definition of the expectation value is just equal to x multiplied by the probability that x equals x. And then we sum over all possible x. And for continuous random variables, we have a similar definition. Right, so something that you will note is that when we go from discrete to continuous, sums change into integrals. And probability functions change into these density functions. Cool. We often write expectational value of x with these symbols mu and mu sub x. Yeah, so sometimes I'll write like EX equals mu. That's all that means. All right, expectation values of transformations. So the expectation value of some g of x transformation of x is equal to the function g of x multiplied by the probability. And for a continuous random variable, it's g of x multiplied by the probability density. Okay? These are just definitions that you kind of just have to remember. It can be a little bit confusing sometimes when you see, when you might see something a little bit more complicated, you might just forget, but come back to these definitions and you'll be doing great. Oops, that has... All right, so more on expectation values. So we've defined this new, I guess, function or relationship, and we should be able to manipulate them. So the expectation value of a constant a is just the constant a. The expectation value of ax plus b is equal to, we can take the a out the front, take the expectation value of the random variable, and then add on b. Then, of course, we can do the same thing if we have two random variables, so A, EX plus B, EY. And if X and Y are independent, this is important, they have to be independent, then expectation value of XY equals the expectation value of X multiplied by the expectation value of Y. Okay, so where do all these relationships come from? Well, we know one thing about the expectation value, which is its definition, so they all come from there. So if you ever forget about one of these, you can always write the expectation value of X equals integral across the sample space of X, fx, x, dx. And for suitable choices of fx, so suitable choices of x, you should be able to derive every single one of these relationships. Except for maybe this bottom one, that might be a little bit, you might have to know a little bit of calculus to split apart the integral, but hopefully it's not too bad. Definition of variance. So, this is one of the other objects in this course, is the variance. So the variance of a random variable is a measure of its spread from the mean. So I guess if we had our random variable, our distribution that looks like that, the expectation value would be around about the mean, and the variance is a measure of how wide this peak is. So what's its definition? Its definition, we just use expectation value of x squared and subtract the square expectation value of x. Right, that's just the definition. Oftentimes in like statistics, especially if you're looking at like a paper, you will hear about the standard deviation a lot more than the variance. The standard deviation is just the square root of the variance, or the variance is the square of the standard deviation. Okay, properties of variance. These are, I guess, useful for if you're doing transformations. So the variance of ax plus b, you take the a out the front and square it. The variance of x is equal to the covariance of x with itself. That's kind of a weird one. Like, we don't usually think about variance and covariance as being like exactly related, but here it is. And the variance of x plus y is equal to the variance of x plus the variance of y plus 2 times the covariance of x and y. Right, so what is this thing covariance? Covariance is something that we're going to meet a little bit more explicitly later, but for now we can just think of it as expectation value of xy minus expectation value of x, expectation value of y. And it's just a measure of if x and y are independent. So if we can imagine combining the variant x and y together, if they're not independent, then this relationship we had earlier will not hold. And so the variance is going to be different by exactly how big that difference is. I hope that makes sense. A little bit of a word salad there, but basically all you need to know is we have these formulas and they get used. If you can just have to kind of memorize them, and you're gonna do well. All right, let's do a question, just because we've met a lot of things and we should know how to manipulate them in the context of a question. So, suppose x is a continuous random variable with probability density function this. Our first part of this question is to find the value k such that the above function is a probability density function. So, what do we do is we just have to find, what do we know? We know that we need to have that the integral across the whole space is going to be equal to 1. So we know that 1 equals the integral across the whole probability space of fxx dx. and that's just going to be equal to integral of k x squared plus 2x plus 1 dx between -1 and 0. Okay, so we just have to perform this integral. Let's do that real quick. So we're going to end up evaluating a third x cubed plus x squared plus x between 0 and -1. I need to have a k out the front as well. That's just going to be minus k, and then I have to sub -1 into all these, so you get, oops. Whoa. We're okay. So we just get -1 on 3 plus 1 minus 1. So that's just going to be k on 3 equals 1. That implies that k equals 3. Cool. So we've done part I. Part II is compute the expectation value of x. So something. Oh, I am getting lag on this machine. Oh, it's fine. Okay. So next thing to do is the expectation value of x equals the integral of x fx of x dx. That equals integral -1 to 0 of x multiplied by 3 x squared plus 2x plus 1 dx. Okay. Well, I can take the 3 out the front, and I can deal with the integral from -1 to 0 of x cubed plus 2x squared plus x dx. Then I can just solve this integral. So it's going to be 4th x to the 4 plus 2/3 x cubed plus a half x squared, 0 minus 1. That's just going to be -3, and then we sub -1 in, so 1 on 4 minus 2/3 plus 1/2. Now, I don't know about you, but I hate doing arithmetic. So at this point, I just sub this into a calculator. I think if we do that, we will end up with, I think it's a quarter. I think it's about a quarter. Minus a quarter? Minus a quarter. I've been told it's minus a quarter, which is correct. I remember. All right, so next thing to do is deal with the machine. The next question was to find the variance of x. So if I go back, compute the variance of x. So how do we find the variance of x? Well, that's just the expectation value of x squared minus expectation value of x squared. Well, sadly, we have to do another integral. And also, sadly, is that this machine is having issues. So let's do, hello, uh-oh. Okay. Well, I guess we just have to find the expectation value of x squared. That equals, well, x squared multiplied by 3 multiplied by x squared plus 2x plus 1 dx. Well, we can just go through this. 3 integral -1, 0. X to the 4 plus 2x cubed plus x squared dx. Just chuck this in as 1 on 5 x to the 5 plus 2 on 4 x to the 4 plus 1/3 x cubed between 0 and -1. Then we can go say -3 and sub in -1. So then we get minus a fifth plus a half minus a third. And you can do the arithmetic at home and you'll end up with something that's like a tenth. All right. So then to get the variance, we can just say that the variance of x is equal to 1 on 10 minus 1 on 4 squared. So it's 1 on 10 minus 1 on 16, which is what? 16 minus 1, 16 minus 10 on 160 equals 6 on 160, which we can simplify if we care to what? 3 on 80. Yeah. So that's how we do this question. This question was also in last year's seminar, so if that wasn't super clear, I hope it should be though. You can have a look at our amazing MathSoc from last year. This question is a new question. Question 14. Suppose f and g are functions of, this is a question from the 2014 question 3B. I think this was the midterm, or it could be the final. I think it was the final. Suppose f and g are increasing functions of, and let x and y be independent, identically distributed random variables with finite expectation. So, right, this is something that we meet often in this course, is independent and identically distributed. And we have to realize what that lets us do. So this whole question is really like a crash course in how do you manipulate these expectation values in a way that was really not super obvious to me when I did this question. So I thought I would teach you how to do it. So first things first, show that f of x minus f of y times g of x minus g of y is always greater than 0. Okay, so and then from this, we have to deduce that the expectation value of that expression is greater than 0. Well, at least the second bit, the deducing, is kind of obvious. If we have the expectation value of a strictly positive random variable, that's always going to be positive, right? So if I draw out like a little diagram, and I have some random variable which is always strictly positive, that expectation value is always going to be positive. Okay? So we can skip after we figure out that this expression is greater than 0, then we automatically get that the expectation value is greater than 0. Okay, well, how do we figure out that this expression is greater than 0? Well, it's kind of, it's all right. We can just say, hey, break it up into two cases. Suppose x is greater than y. Well, we know that f and g are increasing functions, so they're monotonically increasing, and that of course means that if I apply f to both sides of this equation, that means that f of x is greater than f of y. I could also apply g to this equation, so I could have g of x is greater than g of y. Right? So then I can say, well, f of x minus f of y, I guess we could use is greater than, I'm going to use equal signs here, is greater than or equal to 0. And we have g of x minus g of y is also greater than or equal to 0. And so, of course, the multiplication is greater than or equal to 0. Well, what if this condition here is not true? Well, else x is less than or equal to y. Well, maybe even you could say less than y, just to be more accurate. Well, then f of x is less than f of y, and g of x is less than g of y. Oh, I could use a little g, please. g of y. And so f of x minus f of y is less than 0, and g of x minus g of y is less than 0. And that, of course, implies that we're multiplying two negative numbers, so the multiplication is strictly positive. Okay, so it's always greater than or equal to 0. And that's part I. A little bit of just breaking things into parts. So, the next bit is this really ugly question, which is, using the previous results, prove the covariance inequality, which is basically saying, hey, prove this inequality. And this is the bit of the question which is kind of the hardest bit. So, how do we do this? Well, we've got to start off with some ugly algebra. And that is, we have to look at the expectation value of that multiplication. Expectation value of f of x minus f of y, g of x minus g of y. And I'm going to expand this. And what I end up getting is, well, I'm going to have the expectation value of fx gx minus fy gx minus fx gy plus fy gy. Right, so I've just taken that expression and I've expanded inside the brackets. Oh, and now my machine is, yeah, half a second. Okay, so something we know about expectation values is when we have sums, regardless of what they are, we can break them apart. And we also know that this is greater than or equal to 0. Greater than or equal to 0. So we have the expectation value of fx gy oopsies, minus the expectation value of fygx yg of x minus the expectation value of fx gy plus the expectation value of fy g of y. That is always greater than 0. And again, I have to struggle with my machine. Okay. That is greater than or equal to 0. Well, it looks like we have a huge mess. And we do. We do have a huge mess. But it's going to get nice very quickly now. So, what do we know about x and y? We know that x is IID, x and y are independent and identically distributed. Okay? So, in particular, that means that... Uh-oh. Okay. Something goes wrong sometimes. X and Y are IID. I think it's just because I am... OneNote does not like having so many notes. Yeah. No, that could be it. That could be it, yeah. Anyway. Basically... that means that fy and fx are the same function. And they're also independent. So I can write, so there are a couple like facts that we can use here. Since they're independent, we can say that this expectation value here and this expectation value here can be broken up. right? Because we're multiplying two functions that are independent. So a transformation of y and a transformation of x, those are going to remain independent. You can show that mathematically if you look at, well, that's actually really difficult. It's slightly difficult. What you can do is you can consider the inverse functions of f and g to exist, and then you have to look at the definition of stuff, which basically all this means though is that if f and y and g are independent, so I can write this as e of f of y multiplied by e of g of x. And similarly, I can write this as minus expectation value f of x, expectation value g of y. Oh, that one's x? That one is x. Thank you. That is a slight mistake there. Okay. So, what else can we do? Well, we know that the expectation value, the definition of an expectation value, is equal to integral x f x of x dx. Right? So, I also know that fx is equal to fy. So I can write this as integral of x fy of x dx. Right, but here's a trick that shows up a lot of the time in mathematics, is that this is just a label. So I'm going to change out the label, and I'm going to change it to a y. So I'm going to write this as an integral of y fy of y dy. And well, what's that equal to? That's just equal to the expectation value of y. So it turns out that if two variables are identically distributed, we can change out the expectation value of x and the expectation value of y. For something a little bit more explicit, we could also write the expectation value of g of x equals integral gx fx x dx. And then in the exact same way, we can change this into integral gy fy of y dy. Right? All this is to say that I can write a couple of these expressions. I can simplify them down to... I can change out my x's and y's. Right? So instead of y, I can just change everything to x. And that's what I'm going to do. I'm going to write down the expectation value of f x g x. I'm going to take this term now. I'm going to add expectation value of f, y's go to x's, and g, that should be a g of x. Yeah, cool. I'm just checking time. Gx. And then I'm going to subtract off. Well, these two terms become the same because the y comes to an x and this y comes to the x, so it's going to be twice the expectation value of fx, expectation value of g of x. And this is greater than or equal to 0. So we can combine these terms and bring this term over to the other side, and what we see is that we have 2 expectation value fx gx equals 2 expectation value fx expectation value of g of x. Right, so we can divide out by 2, and we are left with the expression that we were looking for. This should be a greater than or equal to sign. It should be a greater than or equal to sign. Please, I don't need this. Uh-oh. Uh-oh. Well. What is an example of f sub x equal f sub y, but x greater than y? Yeah. For the question in the chat, we had what is an example of f sub x is equal to f sub y, but x is greater than y? That's a really good question. Here's how I think about it. When we say fx is equal to fy, what we really mean is that the distribution of the outcomes of the experiments are the same. So if that is the distribution fx, this would be the distribution fy, right? So the green and the black are the same. When we talk about x and y, we're literally just talking about the outcome of an experiment. So x could take this value, or this value, and or this value. X could take on any of these values with the probability going by this distribution. And y could similarly take any of these values, given by just depending on what the experiment comes up as. Let me just turn this off. Right, so we can say that x is greater than y and y is greater than x, while still having that the distributions are the same. Just because in an experiment, we don't know what x and y, capital X and capital Y are. I hope that answers that question, right? So just because the distributions are the same doesn't mean we can't talk about x and y being greater than or less than each other, the outcomes of the experiment. I hope that answers that question. I might have seen it a little bit late. That's okay. We're a little bit strapped for time, so I'm probably going to skip a lot of the questions going forward. They were mostly done last year as well, so if you really want to have a look at these questions, you can look at the amazing Michael Pogg from last year. Moment generating function. So a moment generating function of a random variable x is given by this expression. It is the expectation value of e to the t x. So we can write expectation value e to the t x equals integral e to the t x fx of x dx. Okay, that's the definition of a moment generating function. So this is just the definition. The thing that's useful about the moment generating function is that it's useful to calculate these moments. So instead of having like many different integrals, you can just calculate the one integral and then take derivatives, because we're really good at making derivatives, at taking derivatives. And this is how we get the moment from the moment generating function. We take the derivative with respect to t, and then we take the limit as t goes to 0. So if we go back up to this expression, if I look at like the derivative of d on dt of e to the tx, that's just going to equal x e to the tx, right? And now if I set t equal to 0, so if I say t goes to 0, then this e to the tx is going to go to 1, and so we end up with just x. Right? And that exact logic is why we can use this expectation value, taking derivatives of the moment generating function gives us the moments. It's just because of how taking derivatives of exponentials works. All right, so here is a question about a random variable with probability density function. If I have time, I'll come back to this. there is something really interesting here about finding the expectation value. If I don't get back to it, the trick is that you have to take the limit, because if you sub in t equals 0, you will be dividing by 0. So it's just something to say, hey, when we do expectation values, sometimes you need to take the limit instead of just subbing in t equals 0. That's the trick of that question. We have inequalities. We have Markov's inequality, or Chebyshev's first inequality, which just says that the probability that x, random variable, is greater than a is bounded from above by the expectation value of x divided by a. There's not really too much of a intuition for these kind of inequalities, even this one right here. They're just really things to memorize. I did the course last year and I have completely forgotten these, but hopefully for your exams you can remember them, or hopefully maybe they're on a formula sheet. I don't think so though.
We get our own sheet of notes.
Oh, you get your own sheet of notes? Maybe write these down on those. Yeah, so here is a example problem. So a factory produces 500 machines a day on average, and it's subject to a variance of 100. So we can say that the mean equals 500, and the variance, so sigma squared, equals 100. Find a lower bound for the probability that between 400 and 600 machines are produced tomorrow. Right, so this is something that we've already written out the solution to. So we're looking for the probability that x is between, so we're trying to find a lower bound for the probability that between 400 and 600 machines are produced tomorrow. So we write down the probability that we're interested in. And what we're going to do is we're going to say, hey, I can rewrite this probability as the distance from the mean being less than 100, right? So if I have 500 as my mean, then I have that 600 and 400 are both 100 from the mean of 500. Right, so I'm just writing out my probability in a way where I can abuse Chebyshev's inequality. Right, but Chebyshev's inequality requires this greater than sign. So we have to take 1 minus this probability. And, well, Chebyshev's inequality shows us that this thing is always less than or equal to k sigma. Well, we have sigma equals 10, and we're looking at k sigma equals 100, so k equals 10, and so 1 on k squared equals 1 on 100. Right, so this value is always less than or equal to 1 on 100. And so we just substitute that in, and we find a lower bound given by 99 on 100. Right, I went through that a little bit quickly, but hopefully it's not too bad. Definition of a convex function and Jensen's inequality. So this thing is basically, again, just a thing you have to memorize, just another inequality that they can test you on. Basically, it says, hey, if we have a transformation which is a convex function, then the expectation value, or the transformed expectation value, is going to be less than the expectation value of the transformed function. For this, I'm going to actually refer you to Wikipedia, because there is a, well, they try to do a visual proof of this, and it's really interesting read, but I don't think that it is good for this format, especially since we're so time limited. So maybe give that a little read after the seminar. Just look like Jensen's inequality into Wikipedia. Definition of a convex function. I guess we're just going to skip that for now. It's not too important. All right, common distributions. We've finally gotten through all the ugly bits on random variables, and now we can go through very quickly common distributions. So, for common distributions, formula sheet. Formula sheet is super important. There should have been a formula sheet. Do you have access to that? It's attached to the midterm. This is something that you absolutely want to abuse. It has all the things that are important for these kind of questions. So let's go on to the different distributions. So a Bernoulli distribution is a random variable, models whether a trial will be a success or a failure. So what does it look like? It's just a function that has, at 0, it has height p, and at 1, it has height 1 minus p. All right, so it's just a distribution that tells you about a success or a failure, and we model failure with 0 and success with 1. Right, so it's only one trial, so a trial. A binomial random variable models the number of successes out of n independent trials, each with probability of success p. So if I draw that out, I have two parameters. I have n and p, and those will change the shape of my binomial to look basically something like this. It'll be a little bit peaked. It'll have a peak and then go to 0 as things go out to infinity. And on this x is the number of successes. Right. This is different from a geometric random variable. So notice geometric has only one parameter. And this models the number of trials it takes until the first success occurs. So where binomial was modeling the number of successes, this model is giving us the number of trials until first success, number until first. Okay, what does it look like? I think it looks, it's something, I think, very skewed. It'll look like that. Much more skewed than the binomial. Poisson distribution is, I've got a question. Since we are allowed to bring a formula sheet of our own, what formulas do you suggest bringing into the exams other than the distributions? I think that'll probably be like the remaining things from the seminar, so yeah. Maybe ask, Otto will answer this question later, I think. I've got to get going very soon, so sorry, a little bit rushed. We'll answer that very shortly. A Poisson random variable models the occurrences of a random event, models the number of occurrences of a random event that occurs at a rate lambda on average. So unlike the binomial, Poisson random variables are not bounded above. So if I had a look at the binomial, this would go up to n. Poisson random variables, I guess it looks kind of like that, maybe? I can't remember. I'm not going to write that down. It's very closely related to what we're going to look at a little bit later, the exponential distribution. Yeah, so it models, I guess the thing to remember here is this models the number of occurrences of a random event, so a count. Yeah, cool. Continuous distributions. So, a uniform random variable, this is kind of obvious. We would have learnt about this as, well, maybe you would have learnt about this in like kindergarten. It just is constant. The probability is constant no matter where you are in the distribution. It is equally likely that you will find any value from the experiment. Continuous distributions. An exponential beta random variable is often used to model the time it takes for an event to occur. Alright, so the thing to remember is this is the time it takes for an event to occur. So on the x-axis, if you have something that's like the time, then you're going to want to use an exponential random variable. And it goes off and it looks like something like that. A gamma random variable is the sum of alpha independent exponential beta random variables. Right, so you can imagine a situation where you have to wait for many different events to occur before you see the outcome of an experiment, and maybe each of those events can be modeled by an exponential random variable. And in that case, you're going to have a gamma random variable, a gamma distribution. Right, so I guess you would also be looking at time for time until some success occurs with this distribution. A normal distribution is a very important distribution, and it's used when, well, we'll see more of this. It's just your typical bell curve. When we have little information, we will often assume a bell curve. And that's useful, especially with the central limit theorem. When you have enough trials, things will start to approach the normal distribution. So I guess it's like, I swear there's a good 3 blue 1 brown video on the normal distribution and why it's normal. Maybe give that a look. So, something about the normal distribution, though, is that we can apply a transformation to it. So this is our transformation. And we can standardize it. So a normal 0, 1 distribution can be generated. So if x is distributed as a normal distribution with mu and sigma, we can transform this distribution into a standard normal just by using this transformation. Yep, and a linear transformation of a normal random variable will produce another normal random variable. The beta distribution. So beta distribution is a distribution that models proportions. So thing about the beta distribution is that it is bounded between 0 and 1, and its shape looks something like, it could look like that, it could look like that, it could look, it's much more free, but it's always bounded between 0 and 1. This is its density function, and we write this bottom beta term, this is called the beta function, and it's written in terms of this ugly expression of ratios of gamma functions. Yeah, gamma function is just something that maybe, definitely, should you have a gamma function on your formula sheet? Probably. Maybe, it's so-so. And we have its mean. Okay, so I guess the thing that you want to remember about beta distribution is that it's used to model proportions, so maybe like the proportion of a voter base, or something like that. Could be a question that you're asked. All right, that's the end of bivariate distributions. I think I'm probably... Oh, that's the start of bivariate distributions. We're going to go on to bivariate distributions. I guess now I'll hand it over to Otto, and he'll take you for the rest of this workshop. All right.
All right, thank you very much, Matthew. All right, so, I mean, I guess I'll begin. Depends helpful, thank you very much. We'll begin with just answering a few quick questions. I mean, with the formula sheet, we mainly just want to bring everything that we find useful to us, everything that we do not just immediately remember. Like, am I going to bring, like, yes, my uniform distribution from 0 to 1 looks like, I don't know, this. Am I going to put that on my formula sheet? Probably not. But when we get a lot more useful and maybe some more unique concepts or just stupidly important things to put on the formula sheet, we're really going to want that. And especially putting this in contrast with Gary's 4-question approach that is provided to us, being question 1 being probability and basic distributions, question 2 being central limit theorem, question 3 being estimators, their properties and methods, and question 4 being confidence intervals and hypothesis testing. We're going to want to use a lot more of our formula sheet concerning with, the later half of the course. All right, so let's get moving. Let's do bivariate distributions. Now, there are a number of ways that we can think of bivariate distributions, a number of ways we can solve them, in fact. But, with this course, we really like one figure fits all. So here's going to be our motivation question for this part of the seminar. So, all right, we have this question from 2014, random variables with joint density function given. We're going to determine the marginal density function. We're going to remember that, okay, I know that y is going to be equal to the integral over x, the domain of x, of f of x, y given x, y dx, right? Because this is essentially summing up along a certain direction. Yep. All right. Once we get that out of the way, we're fantastic. Just going to give a brief run through all of these subparts of the questions, what we're really looking for here. We want to also note that, okay, well, conditional probability, we love it. It is our best friend. And so, we know that f of y given x of y given x is going to be equal to the joint density function divided by the marginal density function. Alright. So, moving forwards, next we're going to ask ourselves, are x and y independent? How are we going to do that? Well, we really want to compare these two things. Because if we know that the probability of an event is equal to the probability of an event given another event, we know that if those two numbers are the same, then we have that those two things are independent, because one doesn't affect the other. Okay, so quick question, just a little notation thing. What does Sx mean? Sx is just shorthand for like the domain of x, right? So when I talk about probability and I talk about Sx, it's just like, okay, let's say that x is allowed within 0 and 100. I'm going to go ahead and say, okay, well, Sx is from 0 to 100, which provides me automatically my bounds for my integral. All right. Okay, next up, we take a peek at the calculation of probability, the probability of x plus y being less than 1. Now, this is going to be an interesting integral, which we'll get to in due time. So, joint density functions, basics, we're pulling them back from, okay, we had one variable, now we have two. How do we deal with this? We know that every probability must have a non-negative value. Simple enough. Fantastic. All probabilities sum to 1. Exact same thing. And then we also have that the probability of x being in like a bubble A and y being in a bubble B is given by the integral within those bubbles. Okay? You can see that we're restricting our integrals within very specific bounds. And this is a really important factor because it allows us to very specifically keep track of what events are we accounting for. All right, so we're going to do part 1 first, marginal density. We know that marginal density functions are the integrals. And so we proceed. I wonder why there's a delta there. Usually we like D, but I mean, I guess it's only with respect to y. It's all right. Okay, so here we are. We know that we've taken the integral of it. We substitute in our value here. We integrate an exponential. We end up dividing by the coefficient. And we end up with 1 over 10 e to the minus y on 10. We're going to speed run through this just a little bit because these examples aren't the most, I would say, academically challenging just yet, but they display concepts and we're happy with them. So, part 2, conditional density. Well, we're just going to cover the basics on conditional probability. We understand, as stated before, that this formula is very, very important. And so, we move forwards. Mind you, as covering from before with what Maths tutor said, we cannot have the marginal density be 0 in this case, because if you say that, okay, probability of A given B, if B never happens, I can't find my value, it doesn't work. Okay, so, once again, conditional expectation and variance, they're going to become important later, but some nifty little tricks that we can use. But, I mean, it's essentially all the same. You're bringing them all into pretty much a single variable calculation, right? Because I've just replaced x with x given y is y. Yep. Very standard stuff. All right. So let's do our best. And then we know that, okay, x and y have this distribution, but in this expression, they're pretty much interchangeable. So from a little bit of a quick thinking, we can say, okay, since they're interchangeable, I know that the cumulative distribution of x is the same cumulative distribution as y. And so from there, we can say f of x equals that, and we know that conditional probability is of this form. We perform our division, and we end up with the exact same thing. This is going to be very handy in a little bit of time. So, are they independent? Well, we recall from before, if they're the same thing, in conditional probability against the other, they are quite literally independent from each other. One doesn't have anything to do with the other. Alright, so this is the one that I really wanted to point out, and it makes me very happy. So, is it independent? Well, we know that cumulative distribution, the marginal density function is given by our value right here. We know that our conditional distribution, or probability density function is given by this, and whoop-de-doo, they are the exact same numbers. Alright, and so, therefore they must be independent, as per our equation. Alright, now, how are we going? Are we happy with it? Alright, fantastic. Let's keep on moving. So, now we start getting to the little tricky bits of this question. How do we calculate the probability of x plus y, the summation of our two variables, being less than 1? So, what we want to do is, we want a way to sum all of our values. Now, the easiest way we can think of this is, okay, let's bring it back down to a kind of discrete example. Discrete examples are fantastic because they allow us to think of things very seamlessly. Now, I've drawn a staircase here and a complement staircase here. If I say that this one is x, this one is y, well, I need to sum these two things. Okay, so if each y value being this length has a certain probability associated to it, I multiply that with a respective probability of x. Okay, and by doing so, throughout all of these values, all these respective boards of x and y, I'm able to determine the total probability that a certain event occurs, taking into account two different variables. And so, we start pushing that into a continuous setting. Okay, so the continuous setting of this is saying, okay, well, I have x is an element from 0 to infinity. Almost committed a sin there, putting a closed bound on infinity. And we know that y, similarly, 0 to infinity. Now, if we want the summation to be less than 1, well, rather, since individual probabilities have a value of 0, we can say that this is less than or equal to 1 and just do our integral stuff how we like. So we say that, okay, well, the probability of this occurring, we take an integral from 0 to 1 because we know that x is only allowed to be at most 1, and both x and y are non-negative, okay? So we're only adding onto our number. We're only increasing it. So this is boundary of x. This is Sx right here. Next we need an integral for what the value of y should be. Well, since we're saying less than or equal to 1, we're going to want y to be every value from 0 to complement x to make 1, right? So we're going from 0 to 1 minus x. And this is going to be our domain of y within this integral, within reason. So I might call it sy dash, since it's given that the summation is at most 1. Okay? All right, so we move forwards. We chuck in our joint probability density function, x, y, and then we've got to make sure that we put our bounds correctly. First, we're calculating with respect to y, so that's going to be dy, and then we're calculating with respect to x. So we're summing in two different directions here. These are our bubbles that we're talking about. Okay, and so we run through this and we end up with our solution. Once we understand how to put these things into integrals, it becomes a lot more intuitive how we want to solve them. And so we can just push forwards. Now, I'm sorry if this invokes a little bit of PTSD from a few students here. This is from this year's midterm. It is actually a very informative question. And what I mean by this is that it tests all the right things that I want to show you guys today. So, first things first, we have a joint distribution function, joint density function, given as c times 1 if x and y are, well, lying within a circle of radius 1, right? And so this lends to a lot of geometric kind of concepts that we can just throw at this. We know this is a circle, and we're talking about, okay, the entire inside of it is uniformly distributed with some density 1 over c, and that's that. So we can go ahead and calculate c. We know that the borders are at 1 and minus 1. Radius is 1. Fantastic. So first things first, we go ahead and say, okay, well, I know that the integral of all my probabilities is 1, so I go ahead and I say, okay, integral from, I'm not going to use an integral on this, it's a circle. So the area equals pi r squared equals pi, so c pi equals 1. C equals 1 over pi. Since I'm saying that the summation of all these values, which are the same value, with an area of 1, is my probability, which sums to 1, and so I divide by pi. So we end up with our value, and we are very happy. That is 2 marks already out of 10. Fantastic. Next, are x and y independent? Well, we can think about this very intuitively, right? We have x and we have y as our variables, denoting an x and y axes. And so what we can do from here is just go ahead and say that, okay, are they independent? Well, when I look at it, I kind of say that, okay, if x is over here, can I get a y that is up here? No, I can't. And therefore, the multiplication of p of x being this value, which is greater than 0, and multiplication of y being this value, also being greater than 0, should be a non-zero value. But it is 0. And so it's kind of a proof by counterexample. Independence is a for all statement. We have multiplication being very happy. So we pretty much just say here, okay, well, we say as, let me just jump to my notes, as the probability of x being something greater than 0.99, as well as y being greater than something like 0.99, so I'm going to put an intersection here. This is not going to be equal to the probability of x being greater than 0.99 times by the probability of y being greater than 0.99. And it's quite simple enough. We move forwards. So, next up, marginal density of y, and hence its expected value. Now this is where it starts getting a little goofy, because we look at our thing and we think about, okay, well, what am I meant to deal with? What am I meant to do in this kind of scenario? The same thing we've always done. So, marginal density of y, we go ahead and say fy of y is going to be equal to the integral, mind you, we use sx here, of f of x, y, xy, dx. Fancy enough? Now, we need to make sure that we define this distribution over all the numbers. And it's already been done for us, but this time we have a very specific constant y. So what is x allowed to be for it to actually have a value? Well, we find that since x squared plus y squared is going to be less than or equal to 1, well, yeah, what does that tell us? It tells us that x is an element of the closed boundaries between the negative square root of 1 minus y squared and the positive boundary of square root of 1 minus y squared. Fancy enough? And so I can just chuck that into my integral. And because I've accounted for where x is allowed, I no longer need that fancy one function, right? That one function that says, okay, you're in a circle. I've just accounted for you being in a circle. So I remove a certain layer of obscurity to this question. And so I can replace bounds on my integral now with just negative square root of 1 minus y squared and positive square root of 1 minus y squared. With c in here, which I know is going to be 1 on pi, and so that is going to be dx. And what we end up with is 2 root 1 minus y squared on pi. Fantastic. All right, so that makes us happy. We can keep moving forwards. Did we understand how we ran through that? Are we happy with that?
I don't think the sample stuff is in 2801.
I mean,
Right? 'Cause I haven't-
yeah, that's all right. I mean, some lecturers might like to throw some geometrical intuition into there, just for the sake of it. The one stuff is just like, it's a funny way to define uniform probabilities over certain special spaces. Because I can say like, okay, let me define 1. Mind you, this is the proper character rather than a bolded one, over a certain set S. And so this is just telling me, okay, if I am inside this set, allocate a 1 to it. It's just a very easy way to think about how does it work specifically. It's accessible in 2901 just because the lecturer enjoys throwing interesting questions at people. And I mean, to their credit, solving interesting questions is pretty fun, but I digress. Let's keep on moving. Okay, so we have find the conditional density f of x given y of xy and deduce the distribution. Okay, so I know that this is going to be equal to, mind you, I'm talking about f of x given y. Oops, that's meant to be a given. We didn't see that. I didn't make the slides this morning. All right, I mean, maybe I did. So we continue moving. This becomes joint density of xy given, well, divided by, because we're essentially changing our sample space now, into the marginal of y. Okay, and funnily enough, we just found that. So we can go ahead and use it immediately. Very intuitive. We love it. And so, but there's a little catch. We still need to define the joint distribution. I'm going to just outright replace c with 1 on pi because I should be. We still need the 1 here. And that's why it's important. X squared plus y squared less than or equal to 1. And we divide that by marginal probability of y, which is 2 root 1 minus y squared, all divided by pi. Pi's cancel, and we end up with a very intuitive answer. So we said this is equal to and we draw it as a set. It's a conditional answer, okay? Because this 1 can just be a 1, but everywhere else it is a 0. So we say 1 over 2 root 1 minus y squared. This is for valid values of y, so y being an element of minus 1 to 1, and x being an element of, you guessed it, minus square root 1 minus y squared to the square root of 1 minus y squared. All right, and then 0 else. Fantastic. We're moving forward quite swimmingly. But we're not just done yet with this question. It is a 3-marker for a reason. It wants us to deduce the distribution of x, given y is y. Well, this distribution can be seen as, okay, when I go to where 1 minus y squared equals 0, probability approaches infinity. Now, this would be the endpoints of our function. But really, this is x given y. It's not with respect to y, it's with respect to x now. And so since y is just a constant term when we're considering x, this is a uniform distribution. And the way that we can think of this is in our circle, we are going ahead and saying, okay, for some value y, I'm going to take a cut right here. And we simply remember that, okay, from beforehand, we discussed that, okay, there's a uniform probability across it all. And so on this little line segment here, which is, f of x given y as y, mind you, this is y as y, we have a uniform distribution across this line. And it's not a super intuitive thing, but it's understanding that we're taking one distribution and forcing it to give us more information, which turns out to be another, which can be pretty cool. Very exciting stuff. Anyways, I promise. That gives us our distribution. Now we want the expectation. Well, it's a uniform distribution, which is, mind you, over an even interval. For every value I have over here, I have the same one on the opposite side of it, and I draw a smiley face. We use a little trick here called evenness and similarity. I love geometric proofs. It gives me that the expected value of x given y equals y. Mind you, this is for all values of y. It's still going to be 0 because I essentially average, it's a nose now, we essentially average our values on the left and right hand side of the y-axis here. All right, so we did the question. Fantastic. We're only got 15 minutes to go. Let's see if we can run through 28 more slides. It'll be a quick one, I promise. Okay, so bivariate discrete questions. So here's our new motivation question. We want to do a discrete question because that's the rest of the content, rest of the important stuff for the first part of this seminar. Remember, we're only going up to transformations here, and so we push forwards. Okay, so first we want to determine marginal distributions. Well, marginal means we take for a certain value, and so we sum it downwards. Mind you, this would be marginal with respect to y when we sum downwards, but we want with respect to x, marginal distribution of x. So we would sum to the right, which is exactly what this slide should say. Never mind, it doesn't. Lucky I covered that. Okay, that is what we do. We sum to the right. We say, okay, probability that x is 0 is going to be a summation of 0.15, 0.12, and 0.06, which gives us 0.33, and thus forth. Simple enough. It was in like the midterm practice examples on Mobius or something ages ago. Anyways, it's a little refresher. We know what we're doing. Are x and y independent? Remember, for independence, we have that the probability of y equals y is equal to the probability of y equals y given x equals x for all x. Okay? Well, x not, I mean, probability not being 0. Anyways, for all x, I don't confuse you. And so, in this case, if x and y are independent, that means that, okay, the marginal probability is the exact same as the given probability. And so, what I do here is I compare ratios. Ratio testing is a little trick that we can use here. Because if I look from here to here to here to here, it tells me that, okay, if x is 1, then the probability of the probability of y being 0 is the same as probability of y being 2. Now, if py equals 2 equals probability py equals 0, mind you, this is all given x equals 1 this time. This should always be a fact, okay, if they are independent. However, it turns out they are not independent because I cannot see the same correlation between them. Essentially, what I just said. All right, part 3, covariance, our best friend. I mean, not really, but covariance, it's a nice way to determine the likely interaction between two different distributions in a funky kind of way. Like, if I'm plotting data is like the best way to think about this stuff. If I have x on the bottom, y on the top, I love x and y, and it looks something like this, I can see there's some kind of positive correlation between them. And so that's pretty much why we use covariance to determine correlation in future use. But essentially, mathematically, we just chuck in a lazy formula and do it ourselves. And so, couple properties, that's the word. But it's nothing we haven't seen before. So we should just keep on getting moving. I'll stay on the screens for a little bit each time, just so that if anyone in the online version has any questions, you can pause the video for adequate amounts of time just to get your bearing. Okay, so we keep on moving forwards. What is the covariance of x and y? Well, I know my marginal distribution. My marginal distribution will tell me my expected values. Expected values will tell me a lot of things. So we just jump back up to the table. We have expected values are going to be the weighted sum of our marginal distributions. That is the main important point I want to get out. And so we go ahead, we say that, okay, we can then deduce the marginal probabilities of y, and therefore we can go ahead and determine E of x and E of y. But we're not done yet. We said before, if we took a hard enough glance, that we need the expected value of xy. So we need to jump back up to our table and say that, okay, xy, I'm going to do a weighted sum of you. This row and this column have zeros in them because there's a 0 up here and there's a 0 up here. So the weight of them is 0 when we consider x times y. Okay? And so we only really need to think about 1, 2, 3, and 4 boxes. Okay? So it becomes 0.12 plus 2 times 0.25 plus 4 times 0.15. And if we stay long enough to do the maths, we end up with 0.18. I think. Yeah. Cool. Let's not be too hasty for the device. All right. Are we happy with that? Fantastic. Please don't be shy to ask questions, especially on the live chat. I will get back to how you do the PDF of the product of two random variables just at the end. Actually, no, I can do that right here. I was preparing just as you asked that question before with Matthew. Okay, so in short, no. In long, we say that, okay, if z equals x, y with some probability distributions, we don't really care about them right now. If we want the PDF of z being, how do we differentiate between big Z and big Z, little z. There we go. This thing, well, we don't just want to do some multiplication, right? Because you can imagine, let's say I have one variable I distribute on one bar, one variable I distribute on this bar. And I can take samples from wherever I like. If I'm going ahead and saying, okay, well, for z equals the product of x and y, if I take this one as x, this one as y, from 0 to those values as some way that I distribute certain variables, and I distribute them maybe uniformly, then I can go ahead and say that, okay, well, to make some value z, some very specific value z, then there is some correlation like this, right? Where I need to take 1 over y, sorry, I need to take z over y as my x value, because as z equals x, y, so x equals z over y. We take this kind of thing, so we end up making it the integral, because mind you, we need to take a summation of infinitely many lines, assuming that this is a continuous probability distribution, because you used PDF in your little question up there. Basically, we continue, domain of x, we take f of x, and then multiply by f of y of, get this, z over x, because that's the very important distinguisher here, because we are essentially summing every probability that gives us this event, right? Because we want, okay, outright, how do I get z to be this value? What's the probability associated with it? I need to associate every probability, every choice of two probabilities that makes that one. It's like going back to our funky graph that we had up above, back in the this one up here. Wow, I'm scrolling a lot. Did I miss it? I think I missed it. Am I losing my mind? I think I'm just losing my mind. Don't worry about it. It was way up higher. Anyways, we go back to where we were. We do our summation. And so this would be what we do to get what you want, okay? The main difference here is the fact that you've mentioned, can I just like multiply two graphs to get the resultant? No, because graph multiplication, apart from this, if we just consider graphical graph multiplication, where it's, okay, I have this one multiplied by that one, it gets bigger. But if you want that kind of thing, you end up doing a division thing, but there's funky stuff associated with it. We shouldn't touch into it too much. But anyways, we enjoy statistical integrals simply because it tells us, okay, if I'm looking at this guy, there's a certain thing that this other guy needs to be to compensate to make what I want, if that makes sense. Anyways, we push into transformations. If there aren't any, or rather, if there aren't too many more questions. All right, so transformations, we have another motivation right here. Our motivation here is for some variable, random variable zi, for I being from 1 till n, let it be identically and independently distributed such that zi is the exponential distribution of 1. And then we want the distribution of yn, which would be the minimum of these values. Well, there are funky ways we can do this. The most preferred way is to go ahead and say that, okay, we want this expression to be algebra, okay? The easiest way to deal with things is to just push it into algebra and see what we find out. What information is there that we can gain? Well, not to give you the answer too fast, but here's the answer. Essentially, by implying this algebraic concept, we can say that the cumulative distribution function of y at some point y is the probability that y is less than or equal to y, which is 1 less than y is less than y. And then we can apply our inequality right here, because all of the z's must be greater than y, big Y, that we're counting. And so we get the multiplication of, mind you, independent variables, okay? Which we know their distribution as provided, which gives us another line that we can just cut straight through, okay? These concepts are very important when we want to save time and cut down on just the sheer amount of mental Olympics that we may otherwise be feeling like doing. The main point here that is to be conveyed is that, okay, we love cumulative distribution functions, and even more so, we love converting them through the use of a probability statement. So by doing this, I can replace with z, and by replacing with z, I can then bring in the cumulative distribution function of z, which makes it a lot more intuitive. Anyways, we end up with 1 minus e to the minus ny. Okay. And so PDF, we differentiate it, we end up with n e to the minus ny. Another motivation. All right. Mind you, for transformations, there's like mainly two formulas. We try and get questions out done. Yep.
Just for like the last question, how did you get f(z)?
All right. So when we're dealing with probabilities, right, we love this symbol, big P. Big P just denotes probability of an event occurring. Now, especially when I go ahead and I say, okay, if y is less than or equal to y, this immediately implies, or rather is immediately equal to, the cumulative distribution of y at that point, little y, okay? Now, similarly, this can be taken as the probability of z1 being greater than y is equal to the probability function, cumulative distribution function, that's meant to be a less than or equal to, because this is just, for example's sake, understanding how these things work, of z1 at y, right? So once we have this point, we can go ahead and say, okay, I know that I can get what I want at a certain point, knowing this cumulative distribution function. I don't know this one yet, so I'm going to put it in terms of something I know. And the information I know is that yn is less than or equal to zi for all i's, yeah? And so from there, I can go ahead and say that, okay, well, inequality moves in this specific direction. It is less than or equal to. So I format it so that I have yn is greater than y. And so I know that there's another greater than or equal to symbol right here for all of these z's, yeah? And so that's how we get this jump into here. Now, we're not just done there. We can go ahead and say that, okay, well, because all of these are independently distributed, we have a product of probabilities, right? And so that gives us this little to the n, okay? And then from there, kind of there's been a little skippage of steps right here, because that should be the probability of zi being less than or equal to y, or rather 1 minus it, to the n, right? That's what should be in this bubble right here. And so then we replace pzi less than or equal to y with the cumulative density function, okay? So it's this kind of acrobatics of, okay, what goes where and when, which gives us this very interesting result, okay? So we really want to exercise as much algebraic manipulation as we should in just getting to what we know, right? So we're able to interact with this question simply on the basis that we can transform this probability with respect to y into a probability with respect to z, which we know. Is that good? All right, fantastic. So we move forwards, and so we let x be distributed as the uniform variables from 0 to 1. Mind you, this means that the PDF equals... Whoa, what happened there? PDF equals 1. And so we show that the negative log of x is similarly distributed to the exponential of 1. Now, there are a few ways we can do this. We could do this the exact same way we just did the previous question, in fact. And the way that goes is we go ahead and we say that, okay, y equals minus log of x. And so we say that, okay, the cumulative distribution of y at y equals probability that y is less than or equal to y, which is equal to the probability that minus log of x is less than or equal to y equals probability that x is going to be greater than or equal to, mind you, I've just swapped the sign because I'm multiplying by a negative number, and e to the x is an always increasing function, and so this means that we have a monotonic increasing transformation, which makes this thing very, very useful. E to the minus y. So, mind you, x is uniformly distributed. And so, what I actually get right here is 1 minus probability of x being less than or equal to, mind you, the equal sign is a little funky, since at a single point it's 0, so we can add or subtract it however we see fit, e to the minus y. CDF of x equals x. Simply because we've integrated 1. And so we have fy of y equals 1 minus e to the minus y. So it's this little acrobatics we've just done to get what we want, showing that f of y at y is equal to e to the minus y. I think. Yeah. Anyways, that tells us what we want, but we're going to do it a slightly different way. We're going to go straight to, okay, we want to know how to properly simplify this thing into a proper formula, something that we can apply willy-nilly. So, given that we have a monotonic function, so monotonic means, okay, we're always going up or we're always going down. There is no stagnation, there's no bibbing and bopping up and down. There's only up, there's only down. Plateauing is a little goofy. But I digress, and it gives us this function. And this is very similar to several variable calculus, where it's like, okay, I'm going to look at how I transform one variable into another, and then multiply it by the speed that it's going. In other words, the derivative right here. Anyways, I digress. We go ahead and we apply that, okay, let a variable v equal to h of x, my function. That function is defined as minus log of x. Minus log of x is always decreasing, because it's negative and it goes like that. Yeah. Always decreasing. Goes like this. Yeah. With like x-axis here. Anyways, we keep on moving. We define x as the h inverse of v, which is the same as e to the minus v. So, we push forwards. And so, since it is monotonic, we immediately have the formula just provided. We sub in our values that we've just determined, and we know that f of x, this is just 1, because it's uniform between 0 and 1. So that gives us e to the minus v, which, I mean, I thought my method was kind of cool, but, I mean, you eat your cake how you like to eat it, even if it's with a spoon. So, therefore, it shows us that v is equal to minus log of x, which is similarly distributed to the exponential distribution at lambda equals 1. There we go. Okay, so that's this one done. Now we need a little bit of a goofy one. We're taking the summation of two variables and we're going to say that, okay, these two variables are exponentially distributed. There's always a few ways we can do this. There's always a certain smarter way. Now, I actually don't know how closely we've defined operations on the moment generating functions, but this is one quick and easy way that we can determine this result. We know that for independent random variables with existing moment generating functions, the moment generating function of the sum of these two variables is equal to the product of them independently. Okay? Now, this is a very useful result, and so we immediately can apply it. We know that the moment generating function of an exponential distribution is given by 1 over 1 minus lambda u. I mean, usually we use s now, but u is a pretty cool number as well. So we have that mgf of x1 plus x2 is then going to be equal to 1 over 1 minus lambda u squared, right? Because we're taking the product now. Fantastic. And so we keep on pushing forwards. It ends up being the exact same thing. And we know that MGF's moment generating functions are very unique to their specific distributions. And so, I mean, that's a cheap way to do the question. I kind of like hammering out just pages and pages of algebra and calculus and integrals. But I mean, the way that I would do this, I would go ahead and say that, okay, I love involution. In this sense, I say that, okay, let y equal to x1 plus x2, right? Now I'm just trying to find the distribution of y. I know that x1, x2 are distributed as the exponential function of, I'm making a mess, lambda. And so, what I have is that the fy of y is going to be equal to the integral from 0 to, I can use infinity here, e to the minus, well, I mean, I'll quickly just put in, come on, there we go, f of x of, mind you, since they're both distributed the exact same way, they share the same distribution, f of x at, I'll say x, and then f of x at y minus x dx. And this simplifies into lambda e to the minus lambda x times lambda e to the minus lambda y minus x dx. We know that the x values here cancel, and so it actually ends up being treated as a constant. This would be up to y, my bad. Since we're adding up to y, and since our exponential functions are only greater than 0. Anyways, we continue. So this would be y, so we end up with y lambda squared e to the minus lambda y. Which, I mean, this just ends up becoming just, it's the exact same thing as the gamma distribution. Alright, anyways. So, next question. Now, this next question is very important in considering the partition of our probabilities, okay? And the reason I say this is because it's not immediately apparent how we're going to do this, right? The way that we want to approach this is once again using convolutions, the kind of method that I just mentioned, right? Where we integrate with respect to one of them, just normally, but then we make the other one account for the difference, okay? And so, since we're integrating between negative and positive infinities, we need to ensure that fx and fy are defined between those infinities. So we're going to end up with piecewise functions, so where it's 0 elsewhere, f of x at interest, right? Yeah, that's what that says. Okay, So, before I start getting just straight hammered into the math, any questions so far? Alright, so we keep on moving, and so, first things first, we do not like saying 2u. 2u is not intuitive because it implies that, okay, do I think of this as 3 variables where one's completely dependent on another? I don't like that. Let's go ahead and just say w equals 2u, so we're just doing w plus v. This makes it so much more intuitive because immediately I know that w is uniformly distributed, not in the same way as u or v. It's really goofy how they used u here, but that's goofy. That doesn't happen. All right. Between 0 and 2. And so the density function, what am I doing here? Density function of w at any point within 0 to 2 is equal to 1 on 2. That's an important fact. So this is achieved through the application of our transformation theorem. We push forwards, and so now we have our function. But we don't know the values just yet. The distribution, we understand, has upper and lower bounds of 0 and 3, because we're adding one number between 0 and 1 and another number 2 times from 0 to 1. Maximum at 3, minimum at 0. But this derives certain cases. And that's very important for our bounds. So, going back to the way that I like to think about these kinds of summations of probabilities, I like to have these little diagrammatical explanations, right? So if I'm trying to make a number between, so I'll call this one w, this one's v, and I'm making x, okay? So if x is equal to, rather if x is an element from 0 to 1, okay, I can use the entirety of v. There's no restrictions on it. It's fantastic. Actually, no, that's not the case. Sorry. You can only go up to where x is, because these values, when you're adding them together, are always increasing. And so I can choose some value of v between 0 and x. So that puts a restriction on this kind of convolution that I'm trying to perform. And so that means, okay, for x being between 0 and 1, I have that f of x at x is equal to the integral from 0 to x. So this is put with respect to v, this is sv prime, of, well, f of v, times f of w of x minus v, dv. Mind you, I need to change the input to my function here to ensure that it matches the summation to whatever my x value is. And so, going from before, this is just 1, this guy is a half, I end up with x on 2. Very intuitive. When we understand what are our boundaries, okay, what are our limiting conditions. Now, if I say instead that x is an element from 1 to 2, I am actually really happy with this, because it means that my value of v is unrestricted. I can make 2 when v is 0. I can make 1 when v is 1, just by altering w accordingly, right? So it's an understanding of how we change these values up and down accordingly, or rather opposingly, when determining this distribution. So for this one, we get f of x is equal to the integral from 0 to 1 of f of v, f of w, x minus v, dv, which is just going to be a half, because we sub in appropriately. But then the tricky bit becomes, okay, what if x is an element from 2 to 3? Well, just before I'd stated that, okay, I can make 2 the worst case scenario when v is 0. That's because w is just big enough. Just big enough. But when I want to make anything bigger than 2, I have that v must be greater than 0, greater than some boundary. In fact, this tells me that, okay, I know that v must be an element between 1 and 3 minus x. That's how I'm going to bound v in this case. It's going to be the most intuitive way that I can go ahead and say that. Love that. Okay. We go ahead and say that this is the fact. That's not meant to be, that's meant to be w, sorry. And this way, no, that's still meant to be x. What am I talking about? Okay. This way, I can now define my distribution x as being lower bounded by 3 minus x until 1. So this way, instead of going from the bottom up, I am picking, mind you, this is still v, this is 0, I'm picking the top half because I need to be at least a certain value rather than at most in the first scenario, okay? So this would be 3 minus x. And I go ahead, put in the same values again and again. And what I get this time, mind you, to remind you, this is 1.5. I end up with 3 over 2 minus x over 2. And that works. It works amazingly. I think. And so, I mean, if we want to go ahead and look at how the slides do it, it's a somewhat similar way when we consider, okay, what are the bounds allowed to be? What are these bounds allowed to be given certain cases of x? We keep on pushing forwards and we get one right. We end up with the other one right. And so, bang on. Mind you, it is always important to note that it is 0 otherwise, okay? Because when we call these cumulative distribution functions or probability density functions, we need to ensure that we are defining it over the broadest domain possible. And so, we have another question. I'm pretty sure this is just about the last one, and we've run just a little bit over time, my apologies, but we get straight to it. Essentially, now we are dealing with something that we haven't dealt with before. U equals y squared. How does this work? Mind you, there's a little mistake with the notation here. It's meant to be f of xy at xy equals x times y. My bad. And so, we determine a Jacobian way of changing variables. Okay, so this is just change of variable substitution redux. And so, we love the Jacobian. Jacobian works in mysterious and magical ways to bring us, okay, I want x and y to turn into u and v. And that way, I can then go ahead and say, kind of in the same way that we spoke about multiplying by the derivative when we're just talking about one single variable transformations of variables. This way it allows a multivariable method as described by higher calculus type stuff. 2111, woo. Okay, so now we want to apply it. Note that we have a very important formula right here because this will allow us to do those kinds of things. Now, Gary would like to remind you that this is not an integrals course by any means, within some reason, but it is more so using integrals to properly understand how we can execute statistics. And so, while this may be a bit unnecessary, we can go ahead and just apply to our heart's content. And so, we determine a Jacobian, we throw it in to the substitution because we have f of x, y equals xy. This is also going to be u on 2 times the square root of v, right? And so that's what we get right here. This guy. We multiply by the Jacobian, to resolve in our answer. Now, this is the final question before a little special gift, okay? Sorry, I lied before. So, essentially, this question is dealing with more of our CDF kind of transformations of variables, okay? So, first off, how do we show that the expected value of, mind you, the normal distribution is 0? The easiest way to think of this, rather than going ahead and saying, okay, let's integrate between infinities, already a bad idea, x times 1 on the square root 2 pi e to the minus x squared on 2 dx. That's never going to be fun. We can just say that, okay, my probability function, my fz is even, okay? Fz minus z. And so, by converging this, I can turn this integral into a subtraction of 1/2 to its other half. Sounds a little goofy, usually is, but it ends up with the expected value of z equals 0 by symmetry. Now, when we allow a functional change, a change of variable right here, a functional transformation, a variable transformation, that's the word, we can show that, okay, if y equals z squared, okay, and I want f of y, I can just apply the same trick as before. F of y equals probability that y is less than or equal to y, which equals the probability that the square root of, actually, I'll say it like this. I'll say that since y is z squared is less than or equal to y. Now, what does this mean? It means that the magnitude of z is bounded by the positive and negative square roots of y. And so I write that as following. So I have minus square root of y is less than or equal to z, which is less than or equal to positive square root of y. Now, this two-way collapse of this probability can be expressed now as probability density function of z. So we take, okay, z is going to be less than or equal to square root of y. So that's this part right here. So this is the upper bounding of my variable. So this gives me, I shouldn't have done double line there, f of z of square root of y. So that's that one. And now I'm lower bounding. So I'm actually subtracting. I'm taking some off the top. Here's my normal distribution. I have between here and here. My f of root y is going to be covering everything backwards, but I only want up to here, so I subtract the rest. Double lined again. So, incredible habit. Fz minus root y. Now, when we take the derivative of this, mind you, that's part B done. When we take the derivative of this, we can determine the density function of y. Now, by taking the derivative, we're taking the derivative with respect to y, mind you. That tells us that f of y at y is equal to, derivative with respect to y tells us we take 1 on 2 square root y of f of z, and then minus 1 on minus 2 root y, f of z at root y here. And so these two things are the exact same value because it's even. We continue moving forwards. It becomes 1 on root y, f of z root y. Okay? And that actually just immediately becomes what we want it to become, which is the square root of 2 pi y e to the minus y on 2, which, funnily enough, is chi-squared, chi-squared distribution with 1 degree of freedom. And that'll be all. Okay, I hope that I haven't rushed this too much in the end. We are holding a second revision seminar tomorrow covering everything further onwards, it will probably be more relevant to the exam content for at the very least 2901. But yeah, hope you guys enjoyed this seminar, and thank you very much for your time. Good luck with your exams.